Okay, welcome back. This is the third mini course you're going to be attending this summer, and it's an introduction to elliptic curves. There are people, I think, in the audience that have never seen elliptic curves, or you have seen elliptic curves of different levels. I'm going to start from the very beginning. In fact, today I'm going to do a speed run through the entire mini course, and I'm going to also put elliptic curves into perspective for you, like why on earth we pay so much attention to elliptic curves. So this lecture is all about why. Why do we study elliptic curves? Okay. So first of all, I have 4 hours in this mini course, but there's a famous quote by my grandpa. Serge Lang was my academic grandfather. I'm a student of David Rohrlich, and David Rohrlich was a student of Serge Lang. And in one of his books, Elliptic Curves, Diophantine Analysis, he says it is possible to write endlessly on elliptic curves. This is not a threat. So it is true, there's just so much to be said because it's a very, very rich theory. And there are lots of books on elliptic curves that I recommend. These are more at the undergraduate level, that being one that I wrote myself. And but this one is a quite a classic of Silverman and Tate, Rational Points on Elliptic Curves. It's a great book. And then there are many other books that are at the graduate level, these being like the standard books that one follows on graduate courses on elliptic curves. If you go to YouTube, I have a full graduate course on a full first graduate course on elliptic curves that follows this book by Silverman, The Arithmetic of Elliptic Curves, which is just a very, very good introduction. This is a picture. I don't know if any of you know Hanson Smith. This book is so good that I still go back and still look up things in this book. And this is Hanson's book, Hanson's copy, where he's cataloged everything in there that he found useful. And you can see it's like chock full of math. Okay, so what is an elliptic curve? I can't tell you what an elliptic curve is without putting it into perspective of why do we study elliptic curves in the first place. So we study elliptic curves because we are interested in Diophantine equations from a very, very long time ago. So Diophantine equations being integer coefficient polynomials, so equations, one equation or multiple equations in coefficients that are, so it's a polynomial equation with integer coefficients. And then once we are there, we have questions to ask. There are many problems that are in number theory that boil down to one of these Diophantine equations, and we want to determine, can we determine if there are, not what are they, but can we determine if there are any solutions that are rational or integral? If so, can we find one solution? Can we find at least one solution? And third, can we describe all such solutions? Each one of those problems is, it spans hundreds of years of number theory history. And there's a lot to be said for each one of those. And in fact, Hilbert's 10th problem of the problems that Hilbert proposed in the year 1900, those problems that we know as Hilbert's problems, as stated over the integer, says, is there a Turing machine to decide if f equals 0, if the Diophantine equation has solutions in the integers? He asked, devise an algorithm that will determine whether there is a solution. In fact, there is a talk, one of the plenary talks at the CTNT conference on Saturday. Jennifer Park from Ohio State is going to talk about this problem, number theory applied to Hilbert's 10th problem. So keep an eye for that. And the answer to that is no. There is no such an algorithm. One algorithm that is generic enough that will work for any Diophantine equation, there is none. And that was quite a bit of a shock, where these logicians came to spoil our fun and tell us, no, there is no such an algorithm. But Well, that is for all Diophantine equations, but we can catalog Diophantine equations, characterize them in some way, and then start working in families of Diophantine equations, and we have made some progress on those. So let me tell you where we are. For example, let me give you some examples of Diophantine equations and rational points. 3x plus 5y equals 1, that's a Diophantine equation, that's a line on the plane. There is a point on that line, minus 3, 2. X squared plus y squared equals z squared, equation we're probably very familiar with. That parameterizes Pythagorean triples. That's a Diophantine equation. There are solutions to that equation. The sum of 3 cubes equals 42. That is, or sum of 3 cubes equals a number. That is a Diophantine equation, which only very recently has found a solution to that equation. We didn't know if 42 was expressible, and now recently Booker and Sutherland found that solution, and that's the simplest solution we know of how to write 42 as a sum of 3 cubes. So this is just to say that, you know, it seems like this Diophantine equation is not much more difficult than that one and that one, but somehow the arithmetic just got devilish in this third problem. So some of the number theory we do is try to understand when are we going to be hit by a heavy solution like that, and when are there simpler solutions to be found. This last example is another example of a curve that a lot of us were very interested in, Diophantine equation that lots of people were interested in, and we finally found what the points are, what the solutions are. There's only finitely many solutions to that Diophantine equation. And for example, 1, 1, 2 is one that we knew had to be there, is what we call CM point. I will talk about CM at some point. Christelle will talk about CM at some other point, and then we'll collaborate and use both directions to come up with something really cool during our courses. So we expected that there were CM points on this curve, and we expected that those are the only points, that there should be the only solutions. And that is such an important problem that it was an Annals of Mathematics problem paper just to prove that that's all the solutions to that equation, to that Diophantine equation. As you know, Annals of Mathematics being the most prestigious journal in mathematics. And this is just for one Diophantine equation, for the points on one Diophantine equation. Of course, Jennifer Balakrishnan is one of the co-PIs, one of the co-organizers of CTNT. And this was some great work that not only, of course, you don't get an Annals of Mathematics paper because you solve this one remote problem, is this, you know, champion or initiated a whole research path on how to solve other Diophantine equations. So very interesting paper. This is one of my most valuable mathematical possessions. It's a Post-it, which Martin Davis, if you remember, Davis, Matyjasevich, Robinson, the logicians that told us, no, there is no algorithm. Martin Davis visited UConn a few years ago, and he gave me this Diophantine equation. It turns out that Matyjasevich's theorem, which is the last step to prove that Hilbert's 10th has a negative solution, he said that if we found there was some, I don't remember very well what the problem, but if we determine the integer solutions of the integer points on this Diophantine equation, then Matyjasevich's theorem could be simplified, or the proof could be simplified via this equation. Okay, so what Diophantine equations can we solve? Where are we in the world of Diophantine equations? By the way, this is what my research area is, which is arithmetic geometry. We are looking at things that are sort of geometric objects, and then we're putting, you know, like the number theory in it and see how they interact. So polynomials in one variable, we know how to find the rational solutions to polynomials. There is a divisibility test that helps us figure out that a rational root is the rational root theorem. M will divide this coefficient, and N will divide that coefficient, and given that this is a Diophantine equation, so those are all integer coefficients. So we know how to do Diophantine equations in one variable, any degree. fantastic. We're already very far along. Polynomials in 2 variables, degree 1. So 2 variables, x and y, but degree 1. All the powers are up to 1. Those are lines. Can we find solutions to lines? Well, if you take an elementary number theory course, I spend, in my book, in this book, I spend a lot of time trying to just figure out what the solutions to those are. You have to develop the entire theory of divisibility, greatest common divisor, Euclid's algorithm, the Bezout identity, to prove that there are solutions to these, if and only if the GCD of the coefficients is a divisor of C. So we know how to do integral points and rational points on lines. Awesome. Let's keep going. Polynomials now, 2 variables, still 2 variables, degree 2. Is there a point? Is there a rational point? This is already heavy lifting. This is almost literally mathematically correct to say heavy lifting, because do you know that at least Keith got a laugh out of that one? So we use what we call the local to global principle, and it says this is a big theorem in number theory that tells you that if there are local solutions for every completion of the rationals, Laurie has been already talking about valuations, and we're going to be talking in several of the courses about completions, QP, the reals. So if there are QP solutions and there are real solutions for every P, so in all completions, then there is a point. And then it's a matter of, well, putting a computer to work and try to find such solution. And when I have those, I know one, then I can find all of the rational solutions using for example, something like this, which is a stereographic projection. Okay, given that I know one, then I can find all the other points using this trick. And well, I didn't say about the integer points. That's a little bit more tricky. And if finding one rational point, determine is there one that already has. You have to prove something like the Hasse-Minkowski theorem. To find integer solutions, you also have to learn things like maybe continued fractions to be able to solve Pell's equation, or some algebraic number theory on quadratic fields. So you can use the norms to figure out what is a fundamental unit in some ring of integers, and then using that unit to generate solutions. So there's quite a bit of also some algebraic number theory to find the integer solutions, determine all the integer solutions. But we know how to do it. So the next step is 2 variables, degree 3. And to our shame, we don't know how to do this. This is where we're stuck. So we don't yet have an algorithm that will determine if there is one point, and there is no algorithm to determine what are all the points. We have some candidates for these algorithms, but in any case, because here's where we are stuck, degree 3 curves, this is what we call an elliptic curve. I'll upgrade this definition a little bit in the next lecture, but for the time being, an elliptic curve or a field F is, first of all, it's a projective. When we talk about Diophantine equations, about curves, we're going to talk about them in projective space. You'll see what that means in the next lecture, maybe. So we have a smooth cubic curve, smooth projectively. So if there are points at infinity, we also have to make sure that those points are smooth. It has to be of genus 1. That means that when you draw it as a complex variety, that is actually a torus. And we ask that it has at least one point, because we don't know yet how to find whether there is a point. Well, at least let's start with one point, and then from there see if we can find all the other points. Okay, so we'll work from there, and that is why we study elliptic curves, because it's sort of like the natural next step where we have already a lot of interesting questions to solve in the theory of Diophantine equations. So some very important fact that this is an application of theorems in algebraic geometry. The Riemann-Roch theorem tells you that actually there is models for these elliptic curves, even that I said any smooth cubic curve, just a generic cubic, has a lot of coefficients, but you can simplify those models to things of this sort. Over any field, there's always a model of this, like this, what we call a Weierstrass model. We can talk about why I call that A6 and not A4 at some other time, but there is some what's that? Not A5, and I called it A6. There's some reason about, well, other stuff that I don't want to get into right now. But what we're interested in are the F rational points. So all the points that satisfy the equation and have coefficients in F. Plus, in this form, when you projectivize this form, you actually only get one more point at infinity. In the projective plane, there's only one more point that belongs to the curve, and it's this one in projective coordinates. All you need to know, if you don't know projective geometry, all you need to know is that this is a point such that every vertical line in the plane goes through this point. Okay, so the projective plane is the affine space plus points at infinity that parameterize directions in the plane, so that now we have points where parallel lines meet. And this is the point where vertical lines meet. And if you know a little bit of projective geometry, then you should try to prove that fact. Okay, so for example, the curve y squared equals x cubed minus x, that curve has only 4 points. These are all the points on that curve, and where O is the point at infinity, 0, 1, 0, and that's it. It doesn't have any more points. What about the curve x cubed plus y cubed equals 1? You can prove that this is smooth projectively. It has a point. Can you tell me a point? Is there a point? 0, 1 is a point, for example, or 1, 0 is a point. So there are points. The smoothness, you can just take derivatives and just sort of use calculus to check that there is no kinks anywhere or there's crossings. It's all the derivatives, all the partial derivatives are defined at every point, and it is smooth. Yes, there's a question. Yeah.
How do the variables in the coordinates correspond to the variables in your homogeneous projective coordinate, like 0, 1, 0?
Right. So let me do this one. So in here, the projective version, I will do more examples of this in the next lecture. But the projective version of this curve is you homogenize to the highest degree. This is 3, so I'm going to homogenize to degree 3. So basically, this one is going to become z y squared equals x cubed minus x squared z. And now, there was x was to the first power, and then this is to the 2. And now you can see that the point 0, 1, 0 belongs to that projective curve, right? If we put x equals 0, z equals 0, and y equals 1, then it's a point that belongs to that curve. And if you try to find, are there any other points? The points at infinity are those that this coordinate, they correspond to those that this coordinate is 0. And when z is 0, that's the only point on the curve.
So if you go back to the previous slide, you had, and you homogenize that, you would get 0, 1, 0 as the solution, right?
Correct. Okay. If I just, you can do the same thing. Just complete every monomial, so it's of degree 3 with powers of z, and then you'll see that 0, 1, 0 belongs to that one. And if you put an arbitrary a, comma b, comma 0, the only point in there is going to be 0, 1, 0, projectively, because it's any multiple of 1 is also.
So you use some digit variables to get this wire cross model, and then you can homogenize to get point 0, 1, 0. Okay,
Right. So because we know that in the Weierstrass form, there is only one more point that is missing. We usually just work with the affine model, and then we know there is only one more point, and that one, we keep track of it. Because when we do point counting, for example, I think Keith was doing some of that today, you have to, for the theorems on point counting, you have to have, keep it into account that you have that point at infinity. Okay, so, yep. So this equation, now this Diophantine equation, x cubed plus y cubed equals 1, it is an elliptic curve because it's a smooth cubic projective, and it has a point, but it's not in Weierstrass form. So there are methods to go to Weierstrass form. In my book, Number Theory and Geometry, in chapter 15, the method is explained in a lot of detail, but it's quite a bit of a mess of a method. So I'm not going to go over that in these lectures, but you can read it in chapter 15. Or if you wait for in the next hour when I talk to you about magma, I'm going to show you how to do these things in magma, how to find models for things that are not in Weierstrass form. We do like things that are not in Weierstrass form. This problem has a long history. When it's a number, a sum of two cubes, you probably recognize this Diophantine equation. That one is related to a famous anecdote of Hardy and Ramanujan about, whether 1729 was a boring number or not. And 1729 is the first integer that has two integer representations as a sum of two cubes. That says that this Diophantine equation has at least two different non-trivial solutions. And then you can start thinking about, well, the generalizations of that problem. This problem is, of course, also related to this one itself. When I homogenize it, what do I get? I get this one, which also has quite a history. It's Fermat's last theorem for the exponent 3. So yeah, we're interested in this one, in this particular one. Like magma, or we do a lot of computations in Weierstrass models, and a lot of theorems are written about Weierstrass models. But I want to study elliptic curves like this one, go to the Weierstrass model, do my math there, and be able to bring it back and say things about this equation. Okay, so we do have ways to do that. So there are changes of variables, which means it's an isomorphism to some other model, in this case, this Weierstrass model, such that it will tell me about how to translate one problem to the other. So we will learn how to do that in this course. Some other examples of Diophantine equations and actual problems that are connected to elliptic curves. So why elliptic curves? Still, I'm going to give you some more reasons. Fermat's last theorem itself was finally solved when people realized that there was a connection that you could construct out of a would-be solution of Fermat's last theorem. You could construct an elliptic curve that had such strange properties that probably didn't exist. And then it took quite a bit more work to prove that those properties were true, that these elliptic curves would have those weird properties. That's the work of Ribet. And then that elliptic curves cannot have those properties. Elliptic curves over Q. The elliptic curves are actually modular, and this curve would not be modular. That was the work of Wiles and Taylor-Wiles. The congruent number problem. The congruent number problem, I'll talk a little bit more about it today, is a problem that has hundreds of years, if not 1,000 years of history behind it, and I'll tell you more about it. The ABC conjecture. The ABC conjecture, or in some parts of the world a theorem, unfortunately, is logically equivalent to a specific upper bounds on an integral solution of Mordell's equation, this equation which also already appeared in Keith's class. So there's a connection between one of possibly the most important conjecture in number theory, the ABC conjecture, and elliptic curves. Hilbert's 10th problem that we've already talked about. We know about Hilbert's 10th. That was the theorem. Matijasevich's theorem was about Hilbert's 10th over the integers. But Hilbert's 10th over other rings is open. So on Saturday again, Jennifer Park will talk about what happens if you're trying to solve Hilbert's 10th over Q, over the rational numbers and over other rings in between. Elliptic curve cryptography. If you use, for example, WhatsApp, that's how I communicate with my family. The encryption end-to-end is through elliptic curve cryptography, the Diffie-Hellman algorithm for elliptic curves. So they're everywhere. How about the congruent number problem? So the congruent number problem, this is not how it was originally phrased. Already somebody mentioned, well, Keith's notes, Keith's excellent notes. Of course, if you Google congruent number problem, one of the first hits is Keith's handout on the congruent number problem. And there you can see the actual historical introduction of this problem, which was not this, but I will leave it at that. But let's introduce it as, well, n is a natural number, is a congruent number when there is a triangle, a right triangle ABC with rational sides and area precisely n. So those are the congruent numbers. So n equals 6 is the area of the 3, 4, 5 triangle. The right triangles, the Pythagorean triples can be parametrized. The right triangles with integer coefficients can be parameterized like this. So EF times a difference of squares like that, this is always a congruent number. So that's a source of congruent numbers. So there are infinitely many of them, of course. And for example, 30 is the area of 5, 12, 13. But not every number is a congruent number. Fermat proved that n equals 1 is not the area of a right triangle, and actually that also proves that every square is not a congruent number. And the number 5 is a congruent number, but it's not one that appears from a Pythagorean triple. So it's not one that appears with integer sides. Do you have a question?
Is the definition of a congruent number is that the area is n, like it is an area of a
Yes. N is congruent if it is the area of a right triangle with rational sides, with a right triangle with rational side lengths. If it is, what I'm saying is that if you take the Pythagorean triples, those are side lengths of right triangles, and those give you some of the congruent numbers, but there are more. For example, the number 5 is the area of a right triangle that has rational sides, but not integer sides. So that was actually discovered by Leonardo Migolo Pisano, who you probably know by some other name, Fibonacci. He found the area, a right triangle of area n equals 5. So when Fibonacci grew up in the north of Africa, learned the north of Africa at the time in the 1200s, which much more scientifically advanced than Europe itself. So when he traveled back, his father was some sort of like a diplomat in the north of Africa. When he traveled back to Italy, he brought the numerals we use today, and he started teaching and he started writing books on how to use them to solve problems. He became somewhat of a celebrity. There was no TikTok at the time, but his name did carry. And then the Roman emperor, somebody at the court of the Roman emperor challenged Fibonacci to several problems. So one of the problems that he was challenged with, which means that that problem was already circulating around in the period, was trying to find a triangle of area 5. And he found it. And this is one example of one triangle of area 5. This is actually Keith with Fibonacci. Not that Keith is that old, but with a statue of Fibonacci in Italy. In what city is this? In Pisa? There you go. So there's a very nice statue to Fibonacci over there. Okay, so what is the connection between congruent numbers and elliptic curves? It turns out that there is a correspondence between triples, rational triples, such that a times b over 2 is n, and that they satisfy Pythagoras' theorem. So side lengths of right triangles and points on that elliptic curve. On this elliptic curve in particular, there's this connection given by as follows, that a triple will give you a point, and a point will give you a triple. Okay? So if you want to find points, for example, so if you wanted to find, so this point, the point, or this triangle that Fibonacci found for n equals 5 corresponds to this point on this elliptic curve. Or vice versa, if you didn't know that triangle, you could start with this elliptic curve, find the points, and then use this correspondence to find the triangle. Okay, so there's a lot of also history about this problem and progress that there has been in this area, but let me not get a lot farther into that. It's a very interesting topic. So n equals 5 and this elliptic curve are connected as long as there is a non-zero y coordinate. Of course, look at this. You see that y in the denominators. If you have a point, for example, yes, there is a point. The point 0, 0 is in here. That's not going to be very good. That's not going to give you a triangle. So any point with 5, the 5, 0, minus 5, 0, or 0, 0, which are the points with y equals 0, they don't give you anything. So you want to find other points. So how do you find this triangle? Let me actually grab some chalk. Of course, there's a whiteboard here. So let's draw that elliptic curve. This elliptic curve has points at 0, 0, minus 5, 0, 5, 0. So it goes through those 3 points, and that's a graph of the elliptic curve. Y squared equals x cubed minus 25x. And on that elliptic curve, there is a point in here. That's the point that corresponds to the triangle that Fibonacci found. So I'm going to try to find another triangle of area 5 using just geometry. So what can we do when we have elliptic curves and points? It turns out that there is these geometric constructions that people like Newton already knew, but now we have a much better language to talk about what's happening with those constructions. So this point, what I drew here is the tangent line at that point. That tangent line happens to cross the elliptic curve at some other point. Why would I know that? Well, because this is a cubic curve. You intersect with a line. This is already a double point of intersection. This has to be a third point. And if you know a little bit about how factorization of polynomials work, this actually has to be a rational point also. And it turns out that there is a double point of intersection, and you do find another point on the elliptic curve. And if you use that point with our correspondence, you find a new triangle of area 5. And you can keep this process and find more and more and more triangles. So there's infinitely many triangles of area 5, right triangles of area 5. Okay, so here's again, so this is an example of an elliptic curve. And the key feature of the elliptic curves is that what I just drew is one instance of what we're going to call what we're going to make into an addition law. So there's a group structure on the points on an elliptic curve over a field, and it's based on what I just did. So this is another famous elliptic curve. And on this elliptic curve, there are many points, actually, even with integer coordinates. So here's 2 of them, P and Q. And then you can trace the line, just draw the line from the 2 that goes through 2 of them. And again, because it's cubic and we already know 2 roots, there's got to be a third root, and that root is going to be rational. I'll show you a little bit of that in the next lecture in practice, how that works. And for reasons related to, so that the group law is associative and so on, we actually, instead of picking this point to be P plus Q, we pick the projection or the reflection along the axis. This elliptic curve has an axis of reflection along there, and then do the vertical line and find this other point, and that point is P plus Q. That's how we define the addition on the elliptic curve. And we can also do, like I did before, doubling of points. So if you want to double, you have to do the line that goes through Q and Q, which is the tangent line at Q. And this in red, that's the tangent line. It goes to another point. I'm going to reflect it and pick that one to be 2Q. So that is actually 2Q is that point over there. So that's how we do addition on elliptic curves. And once we have a group structure, then of course we want to know what kind of group do we get. It's easy to prove that it's an abelian group, but what's not so easy to prove, this was a problem that Poincaré proposed to Mordell, and Mordell solved it in 1922. He showed that if you have an elliptic curve over Q, then the group of Q rational points is a finitely generated abelian group. If you've had abstract algebra sort of at the graduate level, then you know there's a structure theorem for finitely generated abelian groups, and that tells you that there's going to be a decomposition. The rational points are going to be, it's going to be a direct sum of the torsion. Those are the points of finite order, and that's going to be a finite subgroup of points of finite order, and then several copies of the integers, which are those points that are of infinite order. We'll talk a lot more about those two things. André Weil, in 1928, generalized this to absurd proportions, but also very interesting, and that's something we also do a lot of research nowadays on too, which is abelian varieties. So abelian varieties is a generalization of elliptic curves. Elliptic curves are the dimension 1 case of abelian varieties, but you can create abelian varieties higher dimension, same concept that there's a group, a structure, algebraic varieties with a group structure. And he showed that the same theorem works for any number field, so things like Q, but also for Q adjoint I, or Q adjoint the square root of 2, or Q adjoint, say, your favorite pth root of unity. An elliptic curve over a number field, over a finite extension of Q, and an abelian variety do have a finitely generated set of rational points. And you can talk again about the torsion, about the rank, and so on. So here are some examples of elliptic curves and Mordell-Weil groups. You can have an elliptic curve with nothing other than the point at infinity is always there, right? So there's no points other than the point at infinity. There is elliptic curves, for example, that only have finitely many points. This elliptic curve has 6 points. This elliptic curve does not have torsion, but it does have a point of infinite order. The point 3,5 is of infinite order. So if you start doing 2Q, 3Q, 4Q, like we were doing before, you start adding it to itself, you get infinitely many points, and they never come back. So there's not a torsion point. It's not a finite order. And then you can mix and match. So this elliptic curve has torsion and it has rank. Okay, so this one, it has a point of order 4, this one, and then 3 points of infinite order that generate the quote unquote infinite part of the elliptic curve. It's not there's no subgroup that is the subgroup of point of infinite order. That's not well defined. But in any case, that's what this represents, is the subgroup generated by these 3 points. So now we have this decomposition, right? And now we can try to characterize what is possible. What can I expect to see? So the first part was trying to figure out what torsion subgroups can we expect. And that was a theorem of Barry-Mazur, a very famous theorem of Mazur, sometimes just called Mazur's theorem. That was conjectured by Levi, sort of forgotten, and reconjectured by Ogg, and then proved by Mazur. And it says that actually for the torsion subgroup, there's not a lot of options. It's one of these. So it can be cyclic of order 1 through 10 or 12. Notice that there is no 11 there. 11 is missing. And there's a beautiful explanation of why that is the case. But in any case, there is no elliptic curve with an 11 torsion point. Or it can be bicyclic. And it can be Z mod 2 cross Z mod 2 or Z mod 4, Z mod 8. Yeah. And each one of those appears infinitely many times. So there's infinitely many elliptic curves with these type of torsion groups. So here's an example of an elliptic curve with a point of order 4. So this point, if you start trying to do this geometric construction, you can show that is actually of order 4. This is an elliptic curve with a point. This point has order 5. This is an elliptic curve of a point. This point has order 6. And I love these constructions. In fact, if you remember anything out of this summer school, is that I have beautiful pictures like this for every torsion subgroup. So if you ever are writing a paper and it's like, oh, I wish I had a beautiful elliptic curve with a point of order 12 that I could fit in this graph. Ah, Alvaro has those. And you text me and I'll send you a copy of my favorite such image. Oh, here it is, a point of order 12. This fat one here, that one has order 12. So there you go. There's a lot of us that are interested still in torsion. You might say, like, why? If Mazer proved that, that's it. Why are you going to Zagreb in Croatia for a conference on torsion? Because, well, Zagreb is beautiful, but moreover, it's because we are trying to also generalize Mazer's theorem to other number fields. So we want to know what happens if now instead of Q I have an elliptic curve over a number field, say Q adjoin I. Well, then you go to Philip Nyman, who is one of the organizers. Where is Philip? Philip. Where did Philip go? There it is. There, Philip. So Philip Nyman proved what can happen over Q adjoin I. Then you prove, and you ask, like, what about Q adjoin the square root of 2, Q adjoin the square root of 17? What about, like the, I don't know, the fifth roots of unity? What happens? So we are working on classifications of what are the possible torsion groups over other number fields. We know what happens over quadratic fields. We know what happens over cubic fields. We don't know what happens over quartic fields. That's open. Who else can I point here to you? So David Zurich Brown is coming to the conference. Harris Daniels is coming to the conference. There's Enrique, who is a collaborator of mine. Jeremy Rouse, he came and he gave a talk before at CTNT. That's one of my older students, previous students. Anyway, oh, Jeffrey Yelton, there he is. He is also coming to the conference. Okay, so there are dozens of us interested in torsion groups. So what about the rank? Well, the rank is a whole other ballpark, and it's very mysterious. So what values can the rank take, and can the rank be arbitrarily large, or is it uniformly bounded? We do not know. However, this is the best rank we have. So the elliptic curve, this huge elliptic curve, Noah Melkis, who spoke here at CTNT a while back, that has rank at least 28. We cannot even prove that the rank is 28 unless you assume the generalized Riemann hypothesis. But we believe this. So we believe the rank is actually 28. So that is the largest rank we have witnessed. And these are points that generate the z to the 28th power. Now, what do we think? Well, in 1950, Neron and Honda ventured that it is actually bounded, that the ranks are unbounded. I'm sorry. Honda and Neron thought that the ranks were bounded. Then a bunch of examples came up that made us believe that the ranks would be unbounded. In particular, there are examples in function fields. Function fields over finite fields are sort of like some distant relative of number fields. So sometimes we think about those because it's easier to prove things there. And now we know that the ranks are unbounded over function fields, over finite fields. We thought, oh, well, that's hope that it's going to be unbounded over Q. But then more recently, other people have ventured that no, that they think like the ranks are actually bounded. More prominently, Jennifer Park, who I already talked about, Void, who gave one of the mini courses at CTNT here a while back. Anyway, Park, Punin, Void, and Wood have conjectured that the rank is actually bounded and that the highest rank is 21. No, they have that there are only finitely many ranks, possible ranks above 21, so that there are infinite families up to 21, but then after that, there's only just a spattering of other ranks possible 28 seems to be one of them. But anyway, they have one conjecture and a beautiful paper where they come up with some heuristic to explain why they expect something like this. Okay, so our goal then is to understand the possible structures of elliptic curves, of rational points, at least over Q. And well, the torsion subgroup is the poster child of what an arithmetic group should be like, well behaved, which is that it's computable. Well, I'll teach you this week how to compute torsion subgroups. It is classified, at least over Q, we have Mazur's theorem. It is parameterized in families. Each one of the torsion subgroups, actually, we know how to come up with all the elliptic curves that have this property. And we even have arithmetic statistics about it, how many elliptic curves are there with a given torsion subgroup. So it is computable because we have the Nagel-Lutz theorem, division polynomials. It is classified again because of Mazur's theorem. It is parameterized in families. For example, if you want elliptic curves with Z-mod 8 torsion, then Kubert and other, so there's family, but Kubert for this one, for example, tells you that if you look at all the elliptic curves with these properties, all of those have a point of order 8. And this is one of my beautiful graphs of an elliptic curve with a point of order 8. And what about statistically understood? Rob Heron and Snowden put out this paper that is great. It tells you exactly how many elliptic curves, if you put sort of like a height on elliptic curves, you order them by what we call naive height, they tell you how many you should expect with a given torsion subgroup. So we know all sorts of things about torsion. How about the rank? Can we compute it? Is it classified, parameterized in family, statistically understood? No, 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 and maybe. So we only computable, we have what we call the descent algorithm, which is not an algorithm because we don't know that it stops all the time. And computationally is a nightmare. So it's not great. And we don't know what ranks happen. We don't know if they are unbounded or bounded, but we don't even know if like up to 28, do they all happen up to 28? We don't even know. So it's a nightmare. So is a rank computable? Analytically, well, yes, again, big asterisk. It's if we assume the Birch-Singleton-Dyer conjecture, then there's an L function, some series that we can write down and then compute the order of the 0 at x equals 1, and that is supposed to tell me what is the rank of the elliptic curve. So you might say that is computational, but it requires some huge number of coefficients to be actually accurate. So the Birch-Singleton-Dyer conjecture is wide open. We don't know. We know some cases where the rank 0 and rank 1, but otherwise we don't know. We don't have it. We don't have BSD. But there is $1 million if you prove BSD, which would be nice. And so that's analytically. What about algebraically? Can we compute the ranks algebraically? Yes, again, a big asterisk. Why is the algorithm not going to work? We don't know that SHA is finite. So SHA is the impediment. SHA is sort of like the roadblocks to this descent algorithm. And descent might fail if for some reason, there was an elliptic curve with an infinite SHA. This algorithm would never stop. It would always keep going to higher, higher, higher descents, and would never find a place where there was no more SHA, there was no more impediments to the local global principle. Basically, SHA, we'll talk more about SHA later on, but SHA measures how much the Hasse-Minkowski theorem fails for elliptic curves. Hasse-Minkowski works for conics in genus 0, but it doesn't work in genus 1. But we are able to measure how far are we from failing. And if this failure is infinite, as you might imagine, then the local to global principle doesn't work very well. Okay, so how does the descent work? The descent, what we do is actually, what we do to compute a rank is we study what we call the weak Mordell-Weil. So we do this quotient of the Mordell-Weil group. And then we embed it into something we call the Selmer group, which is something we can actually compute. And I'll show you a full computation in a second. And then the problem is, if this was 0, that's awesome, because then this is isomorphic to this, and this is computable, so this is computable, right? So the problem is, how not computable is this? So let me show you what happens. So what we're going to do is compute a Selmer group for an elliptic curve. And the Selmer group is actually for a 2 descent. The Selmer group is just a bunch of copies of Zimot 2. And each one of these elements is a Selmer element, and they can be represented by an actual curve. Okay, so it turns out that, for example, for this elliptic curve, the Selmer elements that you need to worry about, or generators of the Selmer group, are these 5 curves. And these green arrows means that there are actual maps, algebraic maps that go from here to here. So if I find a point here, then I find a point here. And any rational point in here of infinite order lives in one of these Selmer groups. Okay? So if I'm able to categorize point here, no point here, no point here, no point here, then I would be done computing the rank. Your hand was first. Yes. Yes. So I don't want to say the word, the C word, the cohomology word, but yes, the Selmer groups and SHA are naturally defined in terms of cohomology. But the cohomology, so yes, cohomology, but no cohomology, because cohomology is, for many of us, a big black box that it's hard to work with. But in this case, cohomology actually works in your favor, because you can actually represent these cohomological elements in terms of actual curves with these coefficients. You can actually make it very explicit. Yes? Are these isogenies? They're sort of isomorphisms. They're sort of like, each one of these is some twist of your elliptic curve. So it's sort of like, in a sense, they're all isomorphic to the original elliptic curve, but they come in different flavors. And then all these maps tell you where all the points land. Okay, so I have all these Selmer groups, and it turns out that this elliptic curve has some 2 torsion. When you have 2 torsion and you're doing 2 descent, those 2 torsion points will show up. So this is a 2 torsion point, this is a 2 torsion point. They had to be somewhere, and those show up. And then this Selmer group actually has a new rational point that I didn't know about. And this one is going to map to a point of infinite order over here. These were of finite order. And then the question is, what's happening here? So what happened here is basically, I did maybe a quick search for points, and you see these have very small coefficients, so I found them easily. Nothing resulted in searching there. What can I do? So these are actually, through the algebraic maps, this point maps to this point maps to here, this point maps to a point of infinite order. Okay? So I have rank at least 1 right now, but there could be more rank with these ones. And what happens is that these 2 are in the SHA. How do I figure out that these are SHA elements? So SHA means that these look like, well, in terms of, like, since we are going to be talking about completions, these ones seem to have local points everywhere. They have points over the reals, they have points over QP every QP. So they look like they should have rational points, but I can't find them. And then I start to suspect, after a larger search on these ones, that they might not have any points. And then what you do is do a farther 2 descent. So I do another descent for this one, and another descent for this one that gives me other spaces to look at. And then in there, prove that actually none of those spaces can have rational points. So these one cannot have rational points, these cannot have rational points, so therefore they're in SHA. So we can actually, by doing a farther descent, I can actually prove that these things are elements of the Tate-Shafarevich group and complete my descent. And what that says is that the Selmer group is 2 copies of Zimot 2 that come from torsion, a copy of Zimot 2 that comes from actual rank, so the rank is 1, and then 2 copies that have arose from SHA, from elements of the Tit-Shafarevich group. And then that's it. That's a whole descent. Now, in a huge, a much bigger picture of what's going on in number theory, what we've done is a tiny bit of what we call now the LMFDB universe. This is a picture that I took from the lmfdb.org website. And elliptic curves is a type of motive. The L function that we talked about, that's an L function that appears here. Connected to the elliptic curves, there are modular forms that I haven't mentioned, but it's a whole other sort of like other side of the world of elliptic curves. So there are modular forms in here. And attached to all of these things, there's also Galois representations, which is actually much of my own research work is in this corner of the LMFDB universe. But elliptic curves is one of the motives, and there's a billion varieties and all sorts of other motives, which is sort of anything that anything that has some sort of cohomology is a motive, essentially. And everything then, it has like L functions and modular forms and Galois representations. And then there's this whole web of connections from one place to the other that many of the talks that you'll see this weekend are in one of these corners or in one of these connections between universes, between worlds. So let me just stop there, and then I'll take questions after I stop the recording. Thank you.